You know, in Finland, there's this hospital information system called ESCO. And here's the thing. It's actually loved by its users. We're talking doctors and nurses who consistently give it the highest ratings, year after year. It's basically the digital heart of the hospital. But what happens when that digital heart, built for one body, suddenly needs to power an entire region? Well, that's the high-stakes engineering story we're diving into today.
Right, so ESCO's success became its biggest challenge. It was a classic good problem to have, but a massive one. Because it worked so well, it got chosen to expand from just one hospital to an entire well-being services county. A huge expansion that created this incredibly urgent technical demand. The system had to scale, and it had to scale fast.
So this was the original setup, the before picture. And honestly, its beauty was its simplicity. You've got your users on the left, this one central server in the middle doing all the heavy lifting, business logic, real-time chats, you name it, and the database on the right. For what it was built for, it was perfect. Clean, elegant, but hiding inside this simple design was a hard limit on how big it could ever get.
And this was the scale of the problem. We're talking about a 12-fold increase in load. 12 times, all within a single year. Now, you can't just go out and buy a bigger server for that kind of jump. That's called vertical scaling, and it gets crazy expensive, and eventually you just hit a physical wall. This is going to require a complete rethink from the ground up.
Okay, so you might be wondering, why not just spin up a few more servers and call it a day? Well, it's not that simple. The moment you go from one server to many, you've created what's called a distributed system, and that opens up a whole new can of worms. The original architecture just wasn't built for that world. A total redesign was the only path forward.
So, what would have happened if they just ignored that and added more servers anyway? Oh, it would have been a disaster. 3 critical failures right off the bat. First, real-time updates, like a crucial new lab result, would only get sent to users on one server, leaving everyone else completely in the dark. Second, every single server would be hammering external systems for the exact same information, creating a traffic jam of wasted work. And finally, the database would have been absolutely crushed under the weight of all the queries.
To really get the database problem, look at this. In the old system, if just one tiny little thing changed for a patient, like maybe they moved to a different room, this server had to go and refetch everything about them. This meant running up to 15 separate queries, pulling data from x-rays, prescriptions, lab studies, the whole shebang. In fact, a single bad query in this process once slowed the entire hospital system to a crawl. Now imagine that mess multiplied by a list of 100 patients. Yikes.
And then you had the polling problem. On the left is the old every server for itself model. If you've got 5 servers, you send 5 identical requests to an external lab system. It's just wasteful. You're clogging up the network, and you risk hitting rate limits from that external service, which could get you temporarily blocked. The goal was to move to the coordinated approach you see on the right. One server makes the request, and then it shares the answer with everyone else. Smart, right?
So clearly, they needed a new blueprint. The team got to work re-architecting ESCO's core, a module known as YTK. The mission? Transform it from that simple, single-server app into a modern, resilient, distributed system that could take whatever was thrown at it.
And here it is, the after picture. Now, yeah, it looks more complex because it's way more powerful. You've got a load balancer at the front, spreading traffic across multiple servers. But the real magic is in the new pieces, a Redis cluster that acts as a super fast message bus and a shared memory bank for all the servers. And the database now has a hot backup, ready to take over in an instant. This, right here, is what an architecture built for scale looks like.
To make this all hum, they brought in 3 key innovations. First, the backplane. Think of it like a central post office. It guarantees that a message sent from one server gets delivered to all the others, no exceptions. Then there's the distributed cache, which is like a shared public library. It holds all the most popular data, so any server can check it out instantly. And finally, the aggregate table. This is a total database supercharger that pre-calculates complex patient info, so retrieving it is lightning fast.
And the results of these changes? They were just staggering. Remember those 15 queries for every patient? Well, to fetch a list of 100 patients, the old system made around 1,500 separate database queries. The new architecture, with that aggregate table, it does it in just 1. That's not an improvement, that's a revolution. Real-time updates now go to everyone, and the data cache is shared and efficient, not locked away on a single server.
But here's the thing.
Building a fast distributed system is one challenge. Building a safe one is a whole different ballgame. With all these different pieces moving at once, the biggest risk is inconsistency. Data getting lost or mixed up somewhere between the database, the cache, and the doctor's screen. And in a hospital, that's just not an option.
So, here's the million-dollar question. How do you solve for that? How do you make absolutely sure that when a doctor updates a patient's chart, that change is perfectly reflected in the database, in the shared cache, and on every single nurse's screen, every time, without fail, even if a server crashes halfway through the process?
The answer is a really elegant engineering solution called the Transactional Outbox Pattern. The best way to think about it is like an indestructible, checkable to-do list that lives right inside the main database itself. This is the secret sauce that makes sure nothing ever gets lost.
Here's how it works. It all starts with step 1, write. When a change is made, the system writes both the change itself and a task describing what to do about it to the database, all in one single all-or-nothing operation. This is so important. Then, in step 2, the servers are all constantly looking at this outbox for new tasks. For step 3, one server grabs a task and does all the work, updates the cache, sends out the message. And finally, step 4, only when every part of that task is 100% done does it delete it from the to-do list. So if a server crashes mid-task, no worries. Another server will just see the task is still there and pick it up later. It's virtually failure-proof.
Okay, so the design is clever, it's safe, but does it actually hold up under pressure? The team put this new system through its paces with a whole bunch of performance tests, simulating the massive load it would have to deal with after the big expansion.
Now this first chart shows something that's actually kind of amazing. They simulated a 6-fold increase in load, and as they added more server nodes, the average time it took for a user to see a patient list went down, from 425 milliseconds with one server to just 282 with 4. That is the absolute textbook definition of horizontal scalability. Adding more horsepower makes the system faster for everyone. And this next chart shows the system's raw work capacity. That red line marks the goal, the 20.8 tasks per second needed to handle the new load. With one server, it couldn't quite keep up. But with 2 servers, it blows right past that goal, and the capacity just keeps climbing in a beautiful straight line with each new server they add. The system proved it could absolutely handle the fire hose of updates.
The final conclusion from the engineering thesis that documented this whole project really says it all. The tests gave them the assurance they needed that this new architecture wasn't just a win on paper, it was a practical success, totally ready to meet the challenge.
So in the end, this was so much more than a software update. It was a complete reimagining of a piece of critical infrastructure to make sure it was ready for the future. And it kind of makes you wonder, right? What other vital systems that we all rely on every single day in banking and travel and government are quietly running on an architecture that's just one big expansion away from a crisis?